Hello general chemistry students. This is the second video in our SLO 5.2. And you recall in the last video we talked about spontaneous versus non-spontaneous process, and we also talked about something called entropy. And we talked about it in the context of a dye mixing in water, and we found that the more opportunities we have to rearrange and have distinguishable states from each other, that we had a higher probability of mixing. And so we can also call this idea of mixing as a disorder that we're going to really in chemical terms call entropy. Okay, and so entropy comes from the second law of thermodynamics. The second law of thermodynamics really states that the entropy of the universe increases, and this has to happen if a process is going to be spontaneous, right? And so when we're talking about the entropy of the universe, really what that means is that we're talking about the entropy of both the system and its surroundings. All right, so remember, we're going back to last semester where we define a system and we define the surroundings. The entropy of the universe is both the system and the surroundings. And for something to happen without outside intervention, the entropy has to increase. All right, so we're going to think of entropy as a measure of randomness of a system. And we used the example of the dye mixing in water before. It really is related to the various modes of motion in molecules, so how many different states those molecules can make. And it's a measure of the heat at a certain temperature, so the dispersal of heat per temperature. So you can think of it as Q over T. All right, and just like the total energy and enthalpy, entropy is also a state function. And so remember, what a state function really means is that it's independent of the path taken. So we will analyze the final entropy, we'll analyze the initial entropy, and of course we're going to talk about entropy in terms of a change in entropy. Okay, so the final minus the initial, because it's a state function. Right, so let's do an example. So we're going to measure the entropy change of a phase change. So heat is going to be transferred, and it's going to be transferred at a certain temperature. So we're going to look at the phase change from liquid water to a gas. All right, so we're going to boil water. What is the entropy for this reaction? Right, so first off, we have to know what the enthalpy, so that's our heat, the enthalpy for vaporization. So this is the enthalpy of vaporization. And we also have to know the temperature at which it boils, which is going to be 100 degrees Celsius. So we can take the enthalpy of vaporization, divide by the temperature of that phase change, and we get the entropy of that phase change. One thing to note is that entropy is going to be calculated in terms of joules per Kelvin mole. Right? That's really going to be really important, because when we start bringing in our term of enthalpy, that's usually measured in kilojoules, but entropy, on the other hand, is usually measured in joules. So we have to really make sure that we're keeping our units consistent. Right? So for an irreversible process, meaning a spontaneous process, the entropy of the universe is greater than 0. If it's reversible, where it can go back and forth, the entropy is 0. All right, so for the second law of thermodynamics, the entropy of the universe must be positive. And to measure the entropy of the universe, we would take the system plus the surroundings. And if in the end the entropy of the universe is positive, then we can say that the process is spontaneous. All right, so we're going to calculate the entropy in terms of energy dispersal in the system and the surroundings. Okay, so we're going to talk about how can we do that. First off, we need to identify the standard entropies. And so the table on the right gives some values of standard entropies. And we can use standard entropies to determine entropies of reactions, just like we did with our enthalpies. And so some things to notice is that the standard entropies will increase with molar mass because we're increasing the complexity of these molecules. And another thing to note is our standard entropies are measured in joules. So pay close attention to those units. And we're going to measure entropy changes just like we did with enthalpies, where we take the products times the stoichiometric coefficient and subtract from it the reactants times their stoichiometric coefficients. And we can measure entropies of reactions given those standard entropies from the table. All right, so let's start. So if we want to measure the entropy for a universe, we will have to measure the entropy of a system and the entropy of its surroundings separately. So first off, we're going to measure the entropy of a system given the standard entropies of our products and reactants. And so we're going to look at this reaction. We have hydrogen and oxygen makes water. Okay? Pay attention to the phase. Okay? So we have gas for our reactants, and we have liquid water. So that's going to be important that we pay attention to the phases. So we're going to take 2 times the entropy of water, liquid water, subtract from it 2 times the entropy of hydrogen plus the entropy of oxygen. And if we look up those values in the table, we can fill those in and calculate the entropy of this reaction. And when we do that, we come up with negative 326.9 joules per Kelvin. And if we think about that, what's happening here is we have 3 molecules of gas that are forming 2 molecules of liquid. So we would expect that the entropy of this reaction is decreasing because gas molecules have more entropy than does liquid molecules, and we're also decreasing the number of molecules as we go to product. So we would expect a decreasing entropy, and that's exactly what we see. All right, so we're not done yet. We have determined that the entropy of this system is minus 326.9 joules per Kelvin. So now we have to measure the entropy of the surroundings. And so how we're going to do that is it's a measure of the energy dispersal. And the measure of the energy dispersal is the enthalpy of the system. So enthalpy is flowing out of the system into the surroundings, so negative enthalpy of the system over the temperature. Okay, so again, we can use those enthalpies of formation to find out what is the enthalpy of the system. So when we do that calculation, we find that we have minus 571.7 kilojoules. Okay, so here we have entropy of the system in joules, and we have enthalpy of the system in kilojoules. So we have to convert to make our units consistent. All right, so we're going to convert to joules, and we're going to divide by the temperature in Kelvin to be 298.15 K. And when we solve for that, we get the entropy of the surroundings to be positive 1,917 joules per Kelvin. Okay, so the next step is to find the entropy of the universe. Right, so we take our system, we add in our surroundings, and we get the entropy of the universe to be positive 1590. And so what we can say about that reaction is that the entropy of the universe is increasing, and therefore this is a spontaneous process. This reaction is going to be product favored, meaning we will proceed to product. All right, so let's take this apart a little bit. So we've defined enthalpies and now we've defined entropies. We will define a favorable entropy to be positive and an unfavorable entropy to be negative. We'll define a favorable enthalpy to be negative and an unfavorable enthalpy to be positive. So there's 4 types of things that can happen. If we have 2 favorable situations, what we can say is that the process is spontaneous at all temperatures because the entropy of the universe is always positive. If we have 2 unfavorable parameters, meaning a positive enthalpy and a negative entropy, this process will be not spontaneous at any temperature. And so what we're going to focus in on is when we have a mixed situation, where we have a favorable enthalpy and an unfavorable entropy, and vice versa. And there we need to measure what is the temperature dependence of the process. All right, and so that's it for this video for entropy. Thank you.